All right, so I would like to begin by thanking the organizers for inviting me to this important workshop. Geoarchaeology is specialized in the micromorphological analysis of soil and sediment thin sections. And I've been extremely lucky to work in Turkey for the past 10 years at a number of Central Anatolian sites. In this talk, I'm going to provide you with a very brief summary of the micromorphological work carried out by myself and several other researchers at the settlements of Bonjuklu and Çatalhöyük dated between 8,300 and 7,800 calibrated BC for Bonjuklu and 7,100, 6,000 calibrated BC for Çatalhöyük. These sites, situated in the Konya Plain and approximately 10 kilometers apart from one another, display well-preserved mud brick architecture and organic residues that have allowed us to shed light into the lifeways of the earlier sedentary communities. I'm also going to cover geoarchaeological sampling at these sites and will share with you the lessons I have learned from the collection of sediment blocks and spot samples in fieldwork. So this slide illustrates the wide range of research topics that can be investigated through thin-section micromorphology, most of which I have explored at both Bonjuklu and Çatalhöyük throughout the years. Starting with consciousness and innovation, these include the characterization of building materials such as mud bricks, mortars, plasters, and roofing materials, as well as their sources within the landscape. Micromorphology has been successfully used to investigate continuity and change in building technologies, spatial boundaries within both open and building areas, and ritual behavior manifested, for example, in ochre or cinnabar plaster coatings and residues. Spheres of interaction and activities comprise research issues that range from concepts and uses of space and the impact of the activities performed on living surfaces or natural deposits, to pyrotechnology and the nature and use of fuel materials. This can shed light into the functional independence of buildings and spaces and contribute to the identification of maintenance practices, periods of disuse, and abandonment of features, structures, and spaces. Discard practices, including sanitation and the accumulation rates of rubbish and redeposited materials, can also be assessed in thin section. Micromorphology has contributed valuable data to studies focused on understanding the complex relationship between plant, animals, and humans, particularly in the early periods leading to the emergence and consolidation of agricultural lifeways. Landscape exploitation strategies, seasonality, and cooking practices have also been explored through the microscopic analysis of fire installations, storage facilities, and associated contexts. Micromorphology has further proven a powerful technique that has allowed us to gain insight into the diet and health of past populations and animals through the microscopic observation of fecal matter and its components and contextual associations. On a more purely perhaps geoarchaeological basis, micromorphology has traditionally been applied to archaeological locations to investigate site formation processes, including the input of anthropogenic versus natural agents in the constitution of archaeological deposits. The determination of the positional environments and climatic reconstructions are themes perhaps more pertinent to earlier periods, such as the Paleolithic, that is the Pleistocene and the Pliocene. And last but not least, post-depositional alterations of archaeological deposits and components such as bioturbation, leaching, diagenesis, mineral replacement, microbial activity, and so forth, can be easily identified through micromorphological studies, thus producing an accurate report of the degree of preservation of the archaeological record at a specific site. The UNESCO World Heritage Site of Çatalhöyük needs little introduction for my Turkish audience, I think. It was discovered in the late 1950s and subsequently excavated by James Mellard between 1961 and 1965. Having to deal with the variability displayed in building furnishings, he distinguished between two types of structures at the site: houses and shrines. The later refer to buildings with large amounts of symbolic features, such as wall paintings, perennia, figurines, and reliefs, that Mellard interpreted as having a primarily religious function. This categorization fell in disuse in the late 1990s as micromorphological analysis conducted by Wendy Matthews and the Ian Hodder's research project demonstrated that all the buildings were lived in, that is, They all showed evidence of domestic occupation, as seen in the micro-residues and artifacts accumulated on living surfaces observed through thin-section micromorphology. These are commonly manifested as dark, fragmented particles of charred materials, also known as soot, trampled and accumulated on top of occupation surfaces, as you can see in the micrographs in the slide. Micromorphological studies at Château-Rieuc have significantly contributed as well to the characterization and classification of clusters on the basis of their microscopic attributes, allowing the identification of similar deposits occurring in different buildings across this very large site. The application of geochemical characterizations through X-ray fluorescence and X-ray diffraction to the plast deposits identified under the microscope resulted in an elemental composition fingerprint for each type. These results allow us to identify extraction locations within the landscape for the collection of construction materials, at the same time as tightly integrating the qualitative data that we get from the micromorphology with quantitative data that we can get from the geochemistry. One interesting conclusion that we reached through this analysis and that allowed us to link environmental change with on-site evidence of subsistence at Château-Rieuc was the characterization of late Neolithic clusters at the site. Significantly, calcareous floors derived from marl sources are substantially coarser in the late built environments excavated at Château-Rieuc than in those observed in earlier buildings at this site. This increase in the sand content of construction materials from the later levels of occupation has been hypothesized to stem from a shift in the exploitation of specific areas within the immediate landscape around the site that was becoming increasingly drier during this period. This would imply that this extraction of fine-grained alluvial soils for the manufacture of architectural materials, those with the highest agricultural potential, was progressively abandoned to allow for their cultivation. As a consequence, other landscape areas likely formed by more finely stratified sequences were systematically exploited for the collection of sources for construction materials, resulting in the mixing of clayish natural deposits such as marl with higher energy strata formed by sandy materials through the extraction process. Another aspect that I would like to highlight about the application of micromorphological analysis to the Central Anatolian Neolithic is the detection of archaeological fecal matter. At Bunjuklu, where isotopic analysis of faunal materials have pointed to the possibility of emerging management strategies leading to caprine herding, aggregates of charred herbivore were identified in the fields of open fire spots. Although the low quantities of fecal materials present in this context and the limited amount of features studied do not allow us to draw conclusions at the moment, one of the research goals that I have currently throughout my Marie Curie project is to explore whether or not this material was being deliberately collected by the first village communities to be used as fuel, as a way of investigating animal domestication trajectories in early sedentary societies different from morphological change. The microstratigraphic sequence of these two samples collected from different sections of space 620, which is quite early in the Château-Rieuc occupation sequence, is illustrative of the spatial variability that we encounter in open spaces at this site. This is visible in the different thicknesses displayed by the various dung layers in each sample. The preliminary micromorphological observations of these slides indicate the deposition of several trampled layers of herbivore dung in this space. Some of these organic deposits contain abundant mineral grains, natural sediment aggregates, and charred plant remains. These are typical components of midden deposits that are here found embedded in these dung laminations, possibly as a result of redeposition and trampling, or more likely to the fact that discard activities were not discontinued in this area during its use as a pen. It is possible then that the alternation that we see in the samples between pen and midden deposits is related to seasonality and life cycles. Also, the discontinuous nature of the dung microlayers in some units might be indicative of the use of only one part of this space as a pen during relatively short-lived episodic events. A combination of these microstratigraphic observations with phytolith extraction and analysis has yielded interesting data regarding the diet of the animals that were kept in this space. These results that were produced by phytolith specialist Marta Portillo point to the presence of well-preserved articulated multi-celled siliceous plant remains derived from Dicotyledonous leaves. This might indicate a diet that is either based on or includes a component of non-herbaceous leaves, suggesting human manipulation of livestock fodder, or alternatively, a selection by obligate browsers such as goats, and therefore might reflect as well some degree of seasonality. Also at Çatalhöyük, micromorphology allowed the identification of several superimposed microlaminations of dungs in space 470 that went completely unnoticed in excavation and that modified the original interpretation of this built environment. These dung remains were rich in partially digested plant matter found in association with thin and highly compacted undulating layers, which suggests substantial animal trampling. The low occurrence of cerolites here can be explained by the accumulation of urine, which increases acidity, and therefore is not a good preservation environment for cerolites. This modest fecal deposit in this space points to its short-lived use as an animal pen, perhaps for sick or birthing animals. Perhaps one of the most interesting results that we have from the earlier site of Punjuklu, also related with the identification of fecal matter in vivisection, which is a topic very close to my heart, is the detection of latrine areas in settlement open spaces, although we originally thought that these images that you can see with field photographs at the bottom and micro photographs at the top. We thought that these were dog or wild boar coprolites, which is a hypothesis that was based on their presence in the zooarchaeological assemblage at the site and the very large quantities of digested bones that were found in these materials. However, the absence of trampling features in thin section, coupled with subsequent gas chromatography mass spectrometry analysis that were carried out at the University of Bristol in association with Ian Bull, allowed us to determine that these were actually human feces. Now, this conclusion had very important implications for sampling strategies at the site, and within time, I mean, these remains are being studied by different specialists, and we hope we can make important contributions to data studies of past human populations, isotopic studies, DNA studies, and so forth. At Çatalhöyük, human coprolites are much less ubiquitous. The oven breakouts of building 162 have been observed to contain omnivore coprolite fragments, some of which had been burned, perhaps to sanitize them. The latest levels were particularly rich in omnivore coprolites and may have been a latrine or an area in which fecal waste was deposited. Significantly well-preserved microbial traces were observed in these materials, both in thin section in the lower image and through fluorescent confocal microscopy at the top. These samples and materials are being investigated by Wendy Matthews at the University of Reading, and results are expected to shed light into the health of the Çatalhöyük dwellers. Last but not least, micromorphology is an invaluable tool for assessing the degree and nature of taphonomic alterations in archaeological deposits. These include bioduration caused by insect and small mammal burrowing, which is particularly destructive to archaeological layers, and also comprises the deposition of excremental pellets and root action. Iron features occur mainly in the form of nodules within the matrix of building plasters, sometimes representing inherited features that form in natural sediment from which the architectural materials were manufactured. Frost features that we have very, very few examples at Çatalhöyük of, but these were detected in a suspected collapsed roof sequence at Çatalhöyük, and they consist of poorly to moderately developed platin microstructures that are produced by temperature-driven desiccation caused by frost, which can open shrinking fissures in deposits below the surface, and in this case confirm our hypothesis of these being actually roof plasters. Precipitation of gypsum salts is really common in arid and semi-arid climates where soil moisture easily evaporates and salts from solution are deposited. I have observed this phenomenon in all the central Anatolian sites I have worked at, with white nodules up to several millimeters in size, often becoming visible macroscopically in the field. So, as you can see in the first photo here. Micromorphology is particularly useful in this case because if we analyze these floor plasters through geochemical methods without an understanding of their depositional and post-depositional environments, we might conclude that these are gypsum-based plasters or that their makers deliberately added gypsum to the mixture for their manufacture, when, as you can see, this is not the case. Moving now on to the practical issues of micromorphological sampling, I have included this slide here displaying space 87, rather a small built environment at Chateau Huyuk, measuring approximately 6 by 2 meters. And the sampling locations and intersections produced to illustrate the high degree of variability that we can encounter in a very small site area. The collection of significant and representative archaeological samples is a common concern for many other techniques, but with micromorphology, this poses particular difficulties. So Danik has also stressed the importance of field research for micromorphologies and how micromorphologies and subsequent stage in field investigations, which is it's really the case. And I'm of the opinion that the best sampling strategy is the one developed between the specialist and the field team. And in the case of micromorphology, we often need to collaborate with excavators to collect desirable samples. This is because we need a section to collect the block from, something that is not always possible, particularly in those field projects that favor open plan excavation. So in these cases, we are left to sample trench edges and negative features such as pits with burial pits such as the one up here at the bottom left, being a particular favorite of mine, or other features such as here at the top right corner where I'm sampling a Neolithic midden deposits inside a later Hellenistic pit that was dug into them. Now, with the collaboration of excavators, it is possible to cross-section and subsequently sample features such as huts and ovens, such as in the top middle picture here. Strategic bolts plinths seem to offer a flexible approach, particularly for building interiors, allowing for the collection of a predictable block sample containing areas of interest with minimum disruption to open area excavation. Occasionally, blocks have to be collected in plants, such as in the case of the bottom right photograph here depicting suspected collapsed roofing materials within building field. In this particular case, as you can see, I failed to obtain a block in my first try. It happens. So I simply moved to the side and used the edge I had created with my first extraction for a second try at the sample. So yeah, it gets tricky sometimes. Regarding sample collection, I normally carve sediment block in the section, leaving some overlap between blocks if I'm collecting several samples. I extract it and then I wrap it in kitchen roll and secure it tightly with tape. This strategy is particularly adapted to clay sequences, such as the one you have in Neolithic settlements in Anatolia. But it might be tricky to apply to coarser deposits, or deposits that have lots of roots, for example. Stabilizing the block sample with plaster of Paris, a plastic container, or even a Tetra brick is a common technique as well, with these materials being easily available in most countries. The only observation I have about plaster of Paris is that it can take some time to dry out, from several hours to a day, day and a half. So it might be tricky to use in wet climates. Cubiena boxes, which are the ones in the bottom right image here, are also very widely used. They should always be gently pushed into the section or carved around, not hammered in, unless we're dealing with waterlogged deposits, because otherwise the sediment will get disturbed and it won't be that useful for micromorphology. These boxes, though, tend to be quite small, and they can be difficult to use in stony deposits when you can get a good fit, or you can have a stone stemming from out, from the edge of the box. Another important aspect to bear in mind is sample packing and transportation. I tend to cut holes in the corners of my sample so that the sediment can breathe, and you don't have too much moisture trapped in that can lead to microbial development and stuff. And then I place the blocks in stiff plastic boxes that are conveniently cushioned with spongy materials. The boxes have to be completely full. This is a very important aspect, because if movement is allowed inside of them, block samples might get scrunched and therefore disturbed. So in extreme cases where the samples were not properly wrapped and properly boxed, this has rendered samples unusable for micromorphological analysis, because they get too disturbed. So I also think when it comes to sampling, it's useful to bear in mind the process that the samples undergo once they're in the lab. So in my particular case, I tend to open the samples once I'm in the lab so that they have a surface to begin to dry out. And I conduct subsampling of the layers that I see after cleaning the block for other techniques such as phytolith analysis and geochemical analysis. So I think something between 1 and 4 grams should be enough. And I recommend people to do this, because then depending on what you find on the slide, you might want to associate with another specialist or send samples to a specialist that can provide more information on those deposits. It's also possible to micro drill the samples, the block samples, once they are resinated and they're hardened. But I think it's preferable to conduct subsampling before they are impregnated with resin. We then introduce resin into the samples under vacuum conditions. Once the sample is resinated and hardened and dry, we cut it. We obtain a 1 centimeter thick slab, we trim it, and then we start the grinding process, mounting into the slide, trimming again, and then grinding to the standard thickness of 30 centimeters. In my case, I have slightly larger samples than Yannick. These images are from the University of Reading laboratory, and we tend to produce what we call mammoth size slides that are 14 centimeters in length by about 7 centimeters in width. Of course, it's very difficult to get a sample this large to the same thickness throughout, so we have to finish it and take it down to 30 microns by hand, which is the last image that you have here. The sponges, diamond sponges that we use to grind the slides for hours sometimes. Thank you so much for listening. All in all, micromorphology is a high resolution technique that enables contextual analysis of forensic scale traces of occupation. This approach brings us closer to the microhistorical scales at which materials and social relations are shaped in the everyday, nowadays as well as in the past. I hope this presentation has persuaded you of the value of these studies for understanding archaeological sites more widely. Thank you very much.